studios in New York City, this is Charlie Rose.
E.O. Wilson is one of the most distinguished scientists in the world. He's also one of my favorite people. Many call him the father of biodiversity. His latest book, The Social Conquest of Earth, considers life's most fundamental questions. Where did we come from? What are we? Where are we going? I'm always pleased to have E.O. Wilson back at this table. Welcome.
Thank you so much.
Good to see you, sir. The book is called The Social Conquest of Earth, which means what?
Well, it means that those creatures on Earth who reached a very high level of social organization.
That'd be us.
That's us.
Right.
That's among the big animals.
Right.
And the social insects, right, and a lot of other small creatures that reach very high levels of social organization.
That'd be ants.
Bees, wasps, ants, termites, and then there are a few others, aphids and so on, that became highly social. Have pretty well taken over the earth.
And by highly social means simply the capacity to live together in groups?
It means living together in groups. We use a special term, eusocial, right. EU, which means good or solid or secure. And we save that word for the societies in which there's a lot of cooperation and some division of labor so that few individuals live longer and reproduce more than the others as part of the social organization. And that's what the ants and bees, wasps, and humans, and a couple of other mammals do. Right. And that's a very interesting phenomenon because it raises the question, if high social organization, which we manifest more than anything else, is so successful, why isn't it more common? So I've raised the question as in that form, and I've also said, why did it take so long to evolve? It took humans most of the history of life, which is over billions of years before we appeared, and the ants, the bees, and the wasps that dominate. I mean, they make up most of the insect biomass, just sheer weight of insects. They didn't appear until, the early age of dinosaurs. It took forever. So the question is, what took so long? And that has led me then to a whole new layer of investigation in which I set out to find out, how did it happen, this thing that took so long?
And? How did it happen?
Well, it turns out that we just haven't been looking in all of our arguments about what's the main force, what's the main circumstance. It preoccupies anthropologists about humans and the like. We should have been looking more carefully, first of all, at all the social organisms in the world to see if there's a general law, just the way we look at gut bacteria.
Right.
To find out the basic of molecular genetics, just as we look at these little roundworms to figure out how nerve cells put together in a brain, we should be looking at all of the different species of animals that have made this huge leap up in evolution to find out what they held in common. And in a nutshell, it is this, and it explains the rarity and why it took so long. They have to go through a series of steps leading up to the threshold before they go from solitary to advanced social behavior. And these steps include one common feature for all of them, and that is the final step is, and it's a solitary species, individuals that are solitary, live together, forms or creates an expensive and valuable nest from which it forages out, gets prey and other food, and brings it back, feeds the young until they mature. Everyone, without exception, of these species that made the jump over into sociality, including human beings, had to go through that process, and that takes a long time.
And so how do you determine who does it and who doesn't do it?
That's the accidents of evolutionary history. We should look at evolution sort of like a maze. You start, say, as solitary, and you evolve. Your species, you evolve. And at some point, the environment is changing or opportunities arise, and you take a turn. You move in a certain direction in evolution. And that might bring you to a dead end insofar as going on to something like advanced social behavior. Or you may, as going through a maze, take the right turn. But only a very few make that right turn. And then the most take the wrong turn. Well, then the correct turn comes up later, and that's a still smaller fraction. So by the time we find that the species are arriving at the point where they can go over and get to the human level, to the ant level, to the bee level, only a tiny percent of all the species that have been evolving for hundreds of millions of years have reached that point where they can cross over.
When you talk about altruism, what do you mean by it in context of take the ants?
Well, in biology we use it in a very special way, and that means that you give up some of what we call genetic fitness. That is to say, you give up some of your expected longevity, or the number of children you're likely to produce, or both, in the service of others in the community. And that's what we call altruism of the eusocial type. That's how these advanced societies get bound together by that type of division of labor based on altruism.
How did you discover William Hamilton's kin selection?
I brought out an article in the Journal of Theoretical Biology in 1964.
64?
Yeah, I read it, and I was first rejected. It was too simple. And I read it again, and I read it again, and then on a train trip going from Boston down to Miami, I was in doing a different kind of field study at that time. I finally said, well, I guess this really is it. So I went over to London at a meeting of the Entomological Society of London and found the forlorn Bill Hamilton wandering around. They turned this thing down for a thesis. He couldn't get his PhD thesis. So I went in with him at the meetings of the Royal Entomological Society and defended him. And subsequently, not just because of that event, but because it was a very good idea, and I'll tell you what it is in a moment, it spread very widely and became actually a productive theory for a while before it began to decay a little bit and break down, and obviously we needed something new. It says essentially that if you are altruistic toward relatives that share genes with you by common descent, you have identical genes due to common descent, you are kin, then you are will enhance your own genetic fitness. That is the fitness of those genes that you have, by contributing something to the close relative. You lose a little bit of your fitness, he or she gains it, and the closer he or she is to you, then the more that person gains from your act of altruism to them. That's what we've been saying for 40 years, and I was one of those that pushed the idea the most strongly in the beginning.
In the
and
academy.
It's very seductive. You know, it seems that is the key to social behavior. The only problem is that it's not true.
When did you come to that conclusion?
Well, I began to see that cracks were appearing in the whole thing.
Yeah.
And the people who were working with it and making it a main subject of their research didn't seem to be able to get outside of a box. They were working just on a couple of the same phenomena over and over again. I won't bore you by telling you what they were. But the theory really hadn't expanded except in statements that someday this will explain this. But I saw that wasn't going anywhere. And furthermore, parts of it just didn't work. Plus, I saw that there were a lot of other explanations for how altruism originated. And I covered this with a series of papers that went from 2006 until, well, for 4 years. and they were mostly ignored, pointing out the flaws and suggesting how a new theory might be formed. And nothing happened until two brilliant mathematicians at Harvard spotted the same thing and came to me, and we collaborated, and it turned out that the basic theory was stated in a form, the original theory, in a form that created a very difficult mathematical problem to get down to the bottom of it to find out whether it was logically true. So they took the effort, made the effort for the first time to go all the way to the bottom, all the way in exploring it fully mathematically, and found it mathematically unsound. At this point, I came in and said, look, also, there's a way of explaining most of the biological phenomena of altruism and helping, and I'll tell you what that is. The new theory says essentially, it's not so much a new theory, it's a revival in a new and stronger form, which says that natural selection, you know, that's the action of the environment that allows some genes to succeed more than others, really is acting at two levels. It's acting at the level of the individuals competing with one another within a society, for the most part, and it's acting at the level of group versus group. And we know now, looking at it a little more with clearer eyes, that group versus group is an absolutely fundamental and overpowering phenomenon in human behavior. It was enough to drive whatever group selection was driving, and what it was driving was altruism and what we call the traits of virtue. That is compassion, willingness to cooperate. I think the evidence is very strong all the way through the most advanced social organisms, including humans, that group selection is the driving force. It's a driving force, and the only one we know of and can conceive that allows authentic altruistic behavior and what we call virtuous behavior among members unrelated to one another in societies, as we expand the theory of the origin of advanced social behavior. And we're putting it on a foundation now that's solidly grounded in biology all the way from molecular genetics, say, to archaeology. That's what's happening. We can really begin to put things together. Now we can approach, once again, the other two great elms of knowledge and research, the social sciences and the humanities, and invite joint examination of what could be called the borderland areas. The characteristics of human social behavior, what we know about the origins and nature of culture and how it's transmitted, and our biological traits, which determine substantially the directions that these various other forms of human evolution have taken.
This is the cover here. It's a Gauguin. So why did you pick this?
I picked it, first of all, because I saw a marvelous opportunity to show the coming connection between the creative arts and science advancing into this domain, and because in Charles Darwin's masterpiece, this is his Tahitian masterpiece, the last great work he did. In the upper left-hand corner, this philosophically inclined artist wrote, it's in French, but I'll tell you what he said.
Tell me what he said.
He wrote up there, where do we come from? What are we? Where are we going? He boldly asked the questions that philosophers long ago abandoned and which science now is left to try to answer.
You like the big questions, don't you?
Well, when you only have several years left to your life, ask them now or never.
The Social Conquest of Earth, Edward O. Wilson, E.O. Wilson of Harvard, one of my favorites. I am pleased to have Dr. Eric Kandel back at this table where he comes frequently. Welcome.
Nice of you to have me here, Charlie.
The Age of Insight. Why call it the Age of Insight?
Vienna 1900 was a very special period in which our view of humankind was altered. Before that, there was a view of human beings as being essentially rational creatures, specially created by God. This was the view of the Enlightenment, to be different from all other animal species. And then Darwin came along and documented how we evolved from simple ancestors and made us realize that there's a continuity in evolution. And the Viennese extended this to pointing out that the human mind is also complicated and not completely rational. There are many irrational components. And the idea of an important aspect of the mind being unconscious mental processes, instincts that control our behavior, emerged in 1900 and emerged from several different influences that I tried to describe here.
Just a bit of history, because it is Vienna, and Vienna is a place that you lived until age 9?
That's right.
What's amazing about this for me, and so then you and your brother left on a boat alone.
That's right.
Your mother had the foresight
Extraordinary.
to feel the fear.
That's right.
And say, early on, work on the visa deal.
Right. And what amazes me is that I was a pretty anxious child, and yet she was able to reassure both me and my brother that everything would be fine. Imagine, at my age, crossing the Atlantic by ourselves. It's amazing, amazing. Yeah.
There's an extraordinary film about this, which is a documentary about your life that captures this. It's also, I take note of this book, is dedicated to the delightful Denise, who deserves it. But what is the role here, as you started to say, of Vienna? This Vienna that you love, because it was the highest, probably the highest representation of intellectual,
modern intellectual life.
Sigmund Freud was there.
Absolutely. On many levels. To begin with, medicine was fairly primitive until 1800. And then in the aftermath of the French Revolution, French medicine began to be scientific. By 1850, Viennese medicine became the dominant force. So it really introduced scientific medicine into clinical practice. And this was led by a guy called Rokitansky, who was the major driving force in the theme of modernism, in my thinking. He was the one that realized that the only way you can make sense out of a clinical examination is to correlate the clinical findings with what you see at autopsy. He said, truths are hidden from the surface. You have to go deep below the skin to find it. Freud was in Vienna School of Medicine in the late stages of Rokitansky's career, and this was the driving theme of his career. You can't simply accept a patient's expression of their illness, psychological description of the illness, as being the only cause of it. You have to go deep into unconscious motivation. And everyone was influenced by the idea that there are things below the surface that you don't see. The painters that I describe in this book, who also developed insights into the unconscious mental processes, didn't want to just paint pretty pictures. They wanted to see, what is Charlie Rose thinking? What's going on in that great mind behind the face? To go deep into it. And you see this at every point along the way.
You have said before, it is the central challenge of science in the 21st century. The central challenge of science in the 21st century is to understand the brain in biological terms. And that's the journey you took yourself.
Yes.
It began,
Yes. And that we are taking in this series.
And doing a series.
Right.
And it's also here, in a sense, connecting the unconscious.
Exactly.
With art.
Right.
And the creative expression.
Right.
And understanding creativity as something.
One thing, this is actually characteristic of what you do and what we try to do together, is to treat science as part of the intellectual enterprise. Why should science be less interesting than golf, baseball, or tennis? It's an extremely interesting intellectual activity, and somehow people are frightened away from science because they think it's difficult. But if you take the pains to explain it, it can be understood by everyone. And what I try to do is bridge between science and the humanities with a specific example, that of Viennese artists of 1900.
I mean, this basic thread running through it all is this sort of interdisciplinary attempt to understand the unconscious, too.
Right. And there was another thing that
As it affects not only the person who creates art, but also the person who observes art.
That's a very good point. I mean, what emerged from students who began to try to put this together, Alois Riegel, Ernst Gombrich, whom you interviewed
Who I
here.
did. The wonderful Ernst
Wonderful,
Gombrich.
wonderful.
One of the great art historians of our time.
But he pointed out that when you look at a painting, you are involved in a creative act.
Right.
What makes a work of art great is ambiguity.
Right.
That you and I see somewhat different things. And the reason we do it is because each of us brings different experiences and a different brain to bear. And we reconstruct the image that we see in our own head.
What do you want us to understand here about the unconscious?
That it is a tremendous influence on both the artist and on the beholder, and that we're beginning to understand how people use both their conscious and unconscious mental processes to respond to a work of art. We can outline a scheme of the various steps that are involved in looking at a great painting and having a perceptual response, an emotional response, an empathic response to it. And we can outline in principle how this occurs. There are a lot of details that have to be filled out, but this is an initial attempt to try to bridge art and brain science.
Ever since I have known you, we have talked about, this C.P. Snow.
Right.
The central question,
Right.
of the relationship between the humanities and science.
Right.
You are a scientist who loves the humanities, yes?
And I love trying to discuss science with non-scientists. And so one of the driving forces for me is to try to get people interested in seeing the bridge between science and the humanities, to realize that knowing a little bit about how facial perception works and how empathy works enriches your understanding of how you respond to art. I think that in the long run, as we know more and more about the biological process involved and how people respond to art, it's not only going to help you enjoy works of art more, but it may even help the artist. Look, Leonardo da Vinci dissected human bodies, so he could see how the muscles exactly attack. So as you learn about the body, he could do a more realistic depiction. As we understand the mind in biological terms, artists may get insights that will really alter the way they depict the psychological sensibility of people.
So what is the question we most want to answer in the pursuit of this bridge?
We want to understand in detail how do different neural circuits get involved in responding to a work of art. There is an enormous recreation that is involved in your brain when you look at a work of art. If we understand that, we will understand an enormous amount about perception. Let me give you an example. You look at a painting, it's two-dimensional. And yet if the artist is successful, you get a tremendous sense of depth if he wants to create perspective. Shows your face, you see it as if it's sculpted, okay? But the brain knows, even though it's recreating this, that it's a flat surface in a painting. And I'll give you a good example. If you have a painting of a person that is made with the artist looking at the subject's eyes, and it's hanging on this wall, and you walk around the painting, the eyes follow you. You must have had that experience many times, okay? If you put a sculpture there and walk around it, the eyes don't follow you. Because the brain knows this is a sculpture, the eyes don't follow you, but it realizes the painting is a fiction. It's a two-dimensional. So this is wonderful to realize how much the brain really unconsciously knows about what's going on, compensates for it, and gives you the sense, but boy, this is really a three-dimensional structure, knowing on one level that it's two-dimensional.
The Age of Insight, the quest to understand the unconscious in art, mind, and brain, from Vienna, 1900 to present. Thanks to Eric Kandel, my friend. Thank you. Pleasure.
Thank you, Charlie.
I am pleased to have Lisa Randall back at this table. Welcome. Why does physics appeal to you?
That's sort of an interesting question. I always liked math. I liked math because it seemed to be definite and predict things, have answers. But the idea of doing just abstract math wasn't as interesting. The idea that you can explain the universe, that you can actually test some of the ideas that you have. Of course, a mathematical theorem can be true whether or not it's realized in the world. But the idea of using using formulas, using math to actually explain and predict and be rational about what is going on in the universe. And the fact that you can explain and predict things, it's a wonderful thing. And so it's really nice to put puzzles together, to have disparate elements that you realize ultimately are connected, and to be able to see how things work.
Knocking on Heaven's Door. Why did you choose that as the title?
Well, as anyone who read my first book knows, I sort of have lyrics that go around in my head when I think of something.
First book was called Warp Passages and Bob Dylan's lyric and all that.
But the first book more had song lyrics as that, like just beginning each chapter. This one I had the song as a title. And it really was because I wanted to express the idea in sort of a fun way of what science does. That you have some base of knowledge that you know, but what science is doing is exploring the edges. It's exploring the things you don't yet know. So you're trying to go beyond that sort of comfort zone to go someplace else. And of course, the lyrics of the song were not referring to that. But I like the idea that you're trying to get to something just bigger than yourself. You're trying to get to something out there that you believe is there. And how do you cross that boundary? How do you cross that threshold to get to some bigger knowledge?
Physics itself. We all are aware of where molecular biology has gone. It has shown us the structure of the DNA. We have mapped the human genome. We have done all these things that have to do with biology. Have we made the same kind of strides, and are we asking what questions in the world of physics?
It's funny because in some ways I'd say that we're in the reverse situation. It's true that we've mapped DNA, but we still have a lot to learn about what that means for animals, for people. What are the implications?
They say the same thing. The journey has just begun.
Right. And in physics, we've actually, we at least know what the rules are down to a certain extent. And what's really wonderful about physics, and this is a point that I think is really important, is that it's sort of systematic, the regime where we understand things and where we need to go beyond it. So we have this core of knowledge that works. And it could turn out that when you explore shorter distances, higher energies, you get to domains that you haven't yet explored, that you find out that fundamentally the rules are very different, but we still have this base of knowledge that works, that makes predictions. I think that we've never reached a point where we have all the answers. I mean, it would be extraordinary for we to be the people that over the course of history just happen to live in a time where we got the theory that works. But I think the other important point is that even if you have a theory of everything, in the sense of you have some fundamental equations that describe some fundamental objects, how to get from there to the kind of phenomena we see in the universe is not a simple problem. To solve those equations to the extent that you can predict all the phenomena. And what you find is that you can't even do it fundamentally in terms of those fundamental ingredients. A lot of the time, you'll need to go into new categories, sort of the way with when we're in the analogy that we had before with throwing a ball versus quantum mechanics. In one case, you're looking at the ball as a fundamental object. In their case, you're looking at the atomic structure. And if you tried to predict a ball using the atomic structure, it would take you a very long time. So it's much more convenient to use the ball. So even if you have the theory of everything that has the most fundamental structure, how that turns into all the phenomena in the world would be very difficult.
Here are two physics questions. I take this glass. It has weight. Do we really understand weight?
Well, we understand sort of functionally what that would mean. We understand what that means in terms of the gravitational force of the Earth, which is really what we're referring to here. But then, again, you could go deeper and you can say, do we know where that mass comes from?
Right.
Do we know what gravity is fundamentally? And the question of where that mass comes from, actually, the mass that is actually being attracted by gravity actually has to do with the strong force, and it has to do with strong interaction, something that's in the standard model of particle physics. But to understand where the mass of those elementary particles comes from, that's what we're turning to the Large Hadron Collider for, among other things.
And tell us about the Large Collider and what we're learning so far from it.
Well, so it's this enormous underground ring, 27 kilometers in circumference.
On the French and Switzerland border.
And what happens is there are two beams of protons, and the protons are accelerated to extraordinarily high energy. 7 times the energy of the machine we're about to close in Illinois. So it's the highest energy we've ever achieved at a collider. And the idea is to have the elements of those protons collide, and when they do, turn into energy via E equals mc squared, which tells us that it can turn into energy.
Einstein's famous formula.
And then that energy can in turn become other particles we haven't seen before. Now that in itself is interesting, but what we're really trying to find out is what is the fundamental structure there? Are there new forces? Are there new ingredients? Could we find this new particle that's associated with understanding how particles acquire their mass? I mean, we know that particles don't just have mass from the get-go. There has to be this new mechanism, this ingredient known as the Higgs mechanism. It's named after the physicist Peter Higgs.
Right.
And it has to do, in some sense, with the fact that there's essentially charge spread throughout space, but not ordinary charge, sort of a charge associated with a different force. And when that happens, particles, by interacting with that, essentially acquire mass. But we know that's the way it should work, but is it really the way it works? And so if it's really the way that it works, there should be evidence. There should be experimental evidence. There should be a particle. That particle is the particle is known as the Higgs boson.
Right. In Knocking on Heaven's Door is also certain ideas about the role of science. What do you want us to understand?
One of the things that I realized when I was talking about War Passages was there are some fundamental scientific concepts that even people really interested in science don't always know. And it's really helpful to have those in mind when, when I talk to my friends, I realize it's useful to have these ways of organizing information, to understand this role of scale, to understand what uncertainty means.
This is about process.
It's about process. It's about the ingredients that go into sort of making a logical, rational decision. It's about understanding that every fact you have comes with uncertainty. And that uncertainty isn't a bad thing. It's part of the statement of the information. It's actually, you understand something only if you understand the uncertainty in what you're saying. And if you listen to debates that go on today, you realize that would be an incredibly important thing for people to understand, because there's sort of a shame associated with having uncertainty, but actually that's part of knowledge. And I think it'd be part of going towards a more rational discussion of scientific facts, but just facts in general.
Some scientists I know and some philosophers I know are worried that in this country, at least, they worry that somehow we have forgotten that. We have forgotten that what science delivers for us, which is fact. That certain things are overwhelmed by the absence of respect for the scientific inquiry.
Well,
And that's the beginning of a decline in the civilization.
That's a grand statement, and it might even be true. But I guess there's part of me that wants to believe that if people have access to the information, if they have access to understanding the method, that they will think in a more rational way, that it won't be the decline of civilization. I mean, part of what I wanted to do was get across some of these ingredients. How do we think about risk? I mean, we've seen nonsensical statements about risk. We've seen some interesting statements about risk, but certainly we tend to be irrational when we talk about risk. And what's going into that? You
travel around the world a lot. Do you find that there's more of an emphasis on science and more of an appreciation? How much of scientific inquiry is simply trial and error?
Well,
I mean, the idea of how do correct scientific ideas ultimately prevail?
Well, how correct ideas prevail is actually interesting, because, of course, anytime you're working on a theory, you don't know if it's right in the beginning. And again, it's a really interesting point. This is something that, again, gets misrepresented about science a lot, because we think of science as, it's all established, and of course, eventually things are established.
Basic laws are established.
Basic laws are established, and they get established over time, and they get tested. And then finally you get to regimes where new things might happen. But in the beginning, I mean, right now, what the Large Hadron Collider will do is it will tell us which theories are right, and it will tell us which theories are wrong. I mean, everyone has ideas about what we might see there, but we don't, and they're not all compatible. And that's fine. It's okay for us to be working on a large number of ideas, because the experiments are difficult and they need to know what to look for. But what's wonderful about having the data is it will tell us who's wasting their time and who should move on.
What is the smallest phenomena in the universe?
What is the
smallest phenomenon in the universe? The smallest, what's the largest?
Well, there's the observable universe.
Right.
And we don't know if that's the largest. It's just that we know the universe that we can observe has been around for 13.7 billion years, and it crosses about 100 billion light years because it's expanded over that time. So there's the size of the universe, But that's not even necessarily the biggest size. Then in terms of the smallest size, there's the smallest size that we can experimentally explore, and then there's the smallest size that we think might exist. And the smallest size we're experimentally exploring is actually at the Large Hadron Collider. High energies lets us look at short distances.
Right.
And that's why going to high...
Can we define those short distances?
Absolutely. And the way we do it, essentially, is if you imagine you have a certain amount of energy, it can create a wave with that energy. And higher energy is shorter wavelength. So basically, to be able to probe short distances, you need something that has structure on that scale. So you need high energy, so you need this high energy wave, and that lets us go to short distance. And that's why we go to these high energies, because it allows us to look at this short distance structure. That doesn't mean that nothing can exist beyond then. There's a difference between what we can think about, what theories tell us, or what theories suggest, or what theories might be possible, and what we can actually observe.
What does all that you know and all that you have learned tell me, how does it inform your instinct as to what is out there that might blow our mind?
Yeah, I'm going to take the fifth on this one, but it's...
Why are you taking the fifth?
Well, I don't know the answer, but
because
the reason
it's a stupid question?
No, it's because actually the most interesting things often were the things none of us thought about in advance. I mean, I think quantum mechanics is mind-blowing to everyone at some level. The idea that...
Why is it? Because...
Well, it's such a fundamental notion that I should be able to say something is here and I can tell you exactly where it's going to be there. The idea that fundamentally there should be probability, I think, is a very big deal. And I think it's always deeply disturbing. It's not that it's wrong, but I think everyone who learns about it is amazed. And no one would have thought of it unless the data told us that's the only way things work. So, and I think in general, even the theory that we came up with about warp geometry, in some sense, we found out that in principle you could have an infinite extra dimension of space. We didn't set out to say, could you have an infinite? It just came out of what we were looking at for entirely independent reasons. So sometimes I just think that the most interesting things, I mean, sometimes the fact of science is more interesting than science fiction.
The argument to be made that the most powerful force in the world is in fact science and not religion.
Oh, that's it. That's it. It depends over what time or for whom and in what sense. I mean, again, it's a really interesting question. Because if you ask what has affected our daily lives more, I'd say for most of us, in some sense, it's science. I mean, just everything we do, everything we do,
which is part of it.
Exactly, and everything, every aspect of our lives. I mean, technology turned off. I mean, we're not living like the Amish, and we really our lives are very different.
Right. Tell me, what is the most important question you guys are asking today? What would be the top 5 questions you think?
I think there would certainly be questions about quantum gravity.
Right.
I mean, aside from the questions we've talked about, how to combine together quantum mechanics and gravity.
Right.
And again, it's really important to realize that this is a question that will have implications at energies very different than any that we can actually observe. So in some sense, it's most likely, in some sense, a theoretical question because it's not clear we can test it.
That's one.
But that's definitely one. I think the question of understanding these questions of mass and how mass is acquired is certainly there,
a big one.
And we have a chance of answering it, which makes it really exciting. The question of what is the missing stuff in the universe? I mean, in terms of what's out there.
The missing stuff. Yeah, that's what I want to know.
That sounds nice.
What is the missing stuff?
Well,
what might the missing stuff be would be my question.
So we know that in the energy in the universe, we know that only 4% is stuff that we're familiar with, the stuff that you and I are made of, the stuff that our universe that we see is made of. But there's this other 96% that's called dark stuff, either dark energy or dark matter, which are 2 different things. So I don't know if that counts as 2 different things that we're looking for.
Yeah. We talked actually about that in one of our previous interviews.
That's
dark
right.
matter.
That's right.
Okay.
And dark matter is also very exciting now in the sense that there really are experiments being set up to really probe some of the interesting regimes and maybe find it, and also some interesting theoretical ideas. But understanding what dark matter is something we have a chance of doing both theoretically and experimentally. Dark energy is a much more mysterious thing. It's just out there. It's a good fraction of the energy. It's 70% of the energy, but we don't know what it is. So I would say that's another very big question that we have.
And which one interests you the most?
Which one? Well, right now, because there are experiments happening, I'm excited about these questions about mass and about dark matter, because there are experiments happening, so we have a chance of learning about it.
How many dimensions are out there, and things like that come under which of those questions?
Well, that's actually, I think I have a fifth left.
All right.
So we can say, what is the nature of space and time out there, in terms of not just how many dimensions there are, but again, this could be a theoretical question. It is a theoretical, but what's out there beyond our horizon? Are there extra universes? Are there other places? And so I think that, but also understanding an extra dimension, sort of squeezing all these into the nature of space and time.
You think we will discover
I think
this?
another question that, I'm going to add one more, though.
Oh, please.
I think
We
there
can
is
get to 10 if you
another
like.
question which is a little bit related to the quantum gravity question, which is sort of what is fundamentally the nature of space and time, which again is something well beyond anything we can do experimentally, but it's certainly a theoretically interesting question.
And the one that interests you the most?
That's a good question. I think it's a really, really interesting question. I think it's very difficult to attack. And I tend to like working on things that I think I have some chance of making progress. So we might get to that, we might get to it peripherally. It's a question in the back of everyone's mind, perhaps, but I think right now the questions are more about how particles acquire mass, why do they have the masses they do.
Jonah Lehrer is here at age 30. He's already a best-selling author. He writes about neuroscience and popular culture in the head case column for the Wall Street Journal. His new book examines a phenomenon that has fascinated humanity for ages, the mind's power to create. It is called, the book, Imagine How Creativity Works. I am pleased to have him at this table for the first time. Welcome.
Thank you.
Creativity. What have you learned about it that we didn't know?
We've had these myths for thousands of years about the creative process, that it's this thing we rely on the muses for. So in a sense, we've outsourced the imagination. I think it just seems so mysterious when we invent an idea out of thin air.
And it was a kind of, it was related to some kind of genius thing.
Yeah, and it's a very rare talent.
Yeah, exactly.
And you see this mirrored in these very sad surveys of school kids where when you ask a second grader, are you creative? 95% say yes, I love to paint, I love to draw. By fifth grade, it's down to about 50%. By the time they're high school seniors, less than 10% of kids believe they're creative.
And what happens?
Well, we are very efficient about killing creativity off in K through 12 education, and that's a very sad fact. But I think they've also come to internalize this myth about creativity, that it is a rare gift. When the science comes with a very optimistic message, which is that creativity is actually a defining feature of human nature. It is a universal talent. This doesn't mean it's evenly distributed. Some people are going to be more creative than others, but it does mean that we can all get better at it.
You say it's our most important mental talent.
Well, we live in a world surrounded by our own inventions. I mean, just look around at this world. It has come to define the human species. This is stuff we all invented. It didn't always exist, and this is the world we live in.
And where does it come from?
You know, it comes from these. It comes from in here. It doesn't come from the muses. The other myth I really wanted to expose that we've had about the creative process for a long time is that we assume creativity is a singular thing, that there is one way we should always be thinking when we need a new idea. Well, it turns out creativity is really a catch-all term for a variety of distinct thought processes, that sometimes you need a moment of insight and sometimes you do need that focus. You need to just grind it out and go through draft after draft.
And sometimes you need a roadblock.
Absolutely. Sometimes it actually helps to hit the wall, to be horribly stumped, because what that's really your brain telling you is you need a moment of insight now. You need a big breakthrough. You need an epiphany. And in recent years, scientists made some very interesting progress in trying to understand where these moments of insight come from. In a sense, they are the most mysterious aspect of the creative process. They've learned, and this required some very interesting experimentation, because, of course, you can't just put undergrads in a brain scanner and say, have an epiphany, we're ready for you. That'd be a very inefficient way to collect data.
We want to look at your creativity. We have the imaging set up.
Exactly. So instead what they had to do was find a way to generate lots of moments of insight on the fly. And what people like Mark Beeman at Northwestern and John Kunios at Drexel have come up with is a set of word problems that generate lots of moments of insight. So these are often known as compound remote associate problems. The acronym is a bit unfortunate, CRAP. But they involve giving people 3 words, and you have to find the 4th word that can form a compound word with those 3. So the 3 words might be pine, crab, and sauce. The answer in this case is apple, pineapple, crab apple, applesauce. And if you find apple, it'll often leap into consciousness just out of the blue. And as soon as it pops into your head, you know this is the right answer. So it feels like a moment of insight. People in the lab will often say, aha, and their eyes go all wide. And what they found is that the seconds before you have a moment of insight, a part of the brain called the anterior superior temporal gyrus, an obscure bit of cortex in the back of your right hemisphere, just behind your ear, shows a sharp spike in activity. And this is a brain area that's been previously associated with things like the processing of jokes and also the interpretation of metaphors. So when Romeo says that Juliet is the sun, we know he's not saying Juliet's a big flaming ball of plasma gas. We know he's using a metaphor. And the way we make sense of that metaphor is by looking past the surface dissimilarities, the fact that Juliet and sons have nothing in common, and instead searching for the underlying themes, those remote associations that they actually share. So we realize Romeo saying that Juliet lights up his world the way the sun lights up ours. Now, a similar mental process is required when you need to make sense of pine, crab, and sauce. Those aren't three words that go together very frequently.
Right.
Yet this one brain area is able to find this one other word, which in this case is apple, that binds them all together. Now, the similar mental process is probably required when we need a moment of insight, because if the connections were on the surface, if they were obvious, we probably would have found them already. That's why we've hit the wall. That's why we're stumped. And so that's why we probably need to rely on this brain area in the back of the right hemisphere, which seems to excel at drawing together distantly related ideas.
It is another word for drawing together distantly related ideas, being able to see connections.
You know, as Steve Jobs once put it, creativity is just connecting things. That is really all it's about. It's a new connection between old ideas. And when you need a big new idea, it's going to come from old ideas that are even farther apart, that no one else can see the connection between them. No one else can bind them together.
What's the relationship between Bob Dylan, creativity, and like a Rolling Stone?
I begin the book by telling the story that happened in May 1965 when Bob Dylan gave up on singing and songwriting. He was so burnt out. He'd been on this grueling tour, and he didn't know how to reinvent himself. He thought he had no songs left to sing. He didn't want to be a folk singer anymore, but he didn't know what to write next. And so he moved up to Woodstock, and he didn't even take his guitar. He was going to paint and write poetry, but he was done with the music business. He's there for a couple days when all of a sudden he feels this familiar feeling, the itch of unwritten words, as he put it. And he says it's like this ghost just gives you what to say. And then he starts scribbling, and his hand doesn't stop moving for the next several hours. He later describes it as like he's vomiting forth these associations, a very, very visceral verb.
And he would be prone to use.
Yes. And then he takes a look at these 25 pages of notes he's scrawled late at night in Woodstock all by himself, and what he sees in these notes are the lyrics to Like a Rolling Stone. The very next week, he goes into the cramped space of Studio A at Columbia Records, and on the fourth take, they record those 6 minutes of raw music that would revolutionize rock and roll.
And he understood it.
He understood
after it came out.
Yeah, and this is a defining feature of moments of insight. This is one of the things that makes them so mysterious, is that as soon as the answer pops into our head, we know this is the answer.
You recognize it for what it is.
You don't have to double-check the math or reread the lyrics. You know this is the solution you've been searching for.
Wow. So suppose suppose you know that you've hit a roadblock. I mean, you've hit a wall.
Yeah.
What ought you do to find a creative way around the wall?
This was quite surprising to me because I think we live in this day and age that worships attention. It's all about the focus.
Right.
So when you hit a hard problem, you assume that what you need to do is to drink a triple espresso, to chug Red Bull, to find some way to increase your attention, to just chain yourself to your desk. That turns out to be exactly backwards. Instead, what scientists have found is that people who are in a relaxed state of mind are much more likely to have a moment of insight.
People say to me all the time, best ideas I had, either I was out running in the morning, I was commuting in my car.
In the shower? The shower's a popular one.
I was hanging out on a Sunday morning, just that kind of thing.
Yeah, and
what is it about that?
Well, because when we're not relaxed, when we're chained to our desk, our attention's out here. It's consumed by the noise of the world. So we're thinking about the problem itself. So to go back to those compound remote associate problems, we're thinking about pine, crab, and sauce. There's probably a wrong answer we just can't get past. It's not until we're relaxed in the shower or on the jog or driving our car that we're finally able to turn the spotlight of attention inwards, and that's when we hear that quiet voice coming from the back of our head giving us the answer. Maybe that voice has been there for hours or days or weeks. We just haven't taken a moment to listen. So that's why relaxation is so important. The larger lesson here, I think really gets back to this wonderful line of Einstein's that creativity is the residue of wasted time. When you need a moment of insight, you really have to make time to waste time because, and this seems paradoxical, but the answer will only arrive after you stop searching for it.
So there's also Milton Glaser. What do we learn from him? A great designer.
He's got this wonderful slogan above his studio door, which is art is work. And it would be wonderful if the advice we could give to everyone is that, you know, the solution to every creative problem is to take a long hot shower, to go for a walk on the beach, to drink a beer. That's, of course, not how it works in the real world. You know, when you talk to creative people, they often begin with their romantic breakthroughs, those epiphanies that arrive when they least expected it. But then if you press them, they talk about all the hard work that came after. They talk about all the iterations and drafts, all the frustration and failure.
And also their curiosity. I mean, I've talked to really a large number of artists, you know, that just go to the gallery or go to the museum and just look. Yeah. I mean, it's a studying process for them.
I think it's about realizing that creativity is not a straight line, that it really is about just being open-minded. It's about letting yourself be exposed to lots of ideas, even if you don't know how they're going to fit in. It's about seeking out diverse inputs. And you see this mirrored again and again in literature. It's why entrepreneurs with more diverse social networks, people who spend time with lots of people who aren't like them, that according to one measure of innovation, they are 3 times more innovative than people with predictable social networks. So it's great to spend time with people who don't think like us.
What do jazz pianists have?
This is I think for me one of the big mysteries that I was interested in when I began thinking about this book. Is you watch videos of John Coltrane, and this guy just steps out onto a stage and beauty pours out of him for 45 minutes, for 60 minutes, and he's just improvising. He has no idea what he's going to play, and yet he just knows he can invent it. And
could he duplicate it the next night?
Well, he could create a whole new kind of beauty the next night. And this is totally awe-inspiring. And, you know, there's some really interesting new work which has begun to deconstruct the improv process, this kind of spontaneous creativity. And what these scientists have discovered, these are scientists at Johns Hopkins, is when you put jazz pianists inside a brain scan and you ask them to improvise, that they begin by inhibiting their inhibitions, that they, in a sense, deactivate a part of the brain called the dorsolateral prefrontal cortex, which is just behind the forehead. It's closely associated with things like self-control, impulse control. It keeps us from eating all the ice cream in the fridge. It allows us to not say the first thing that comes to our mind. So it's a pretty important part of the brain, but it can also hold us back because it makes us worried about what we're saying. It's that voice telling us not to do something. And when you need to improvise for an hour on stage, when you need to let yourself go, you need to get out of your head. You need to turn that voice off. And so in a sense, they're able to just inhibit their inhibitions on command. You know, that itself, that act of deactivation takes years of practice. It looks easy on stage when they do it, but that's only because they work so hard.